Welcome back. In this course, I'm going to ask you to design your own space robot while learning about space robots. I think a couple of ways to best learn and verify learning is through demonstration or application. So let's learn about the design process, which you will emulate in the rest of the course. In this lecture, I hope that you'll understand how to design a space robot from mission objectives to system architecture, leveraging techniques developed in systems engineering. This flow block diagram outlines the end-to-end process of designing a planetary robot from the initial idea all the way to the baseline design. This is the framework you'll be walking through in this course, not just in theory, but in practice through a sequence of assignments that guide you step by step. Pretty soon in the next module, I'm going to walk you through and ask you to define a mission objective or scenario based on the latest stakeholder documents. As of this recording, that includes the Planetary Science and Astrobiology Decadal Survey, the annual NASA SPIR/STTR solicitation, and the latest ISRU Gap Assessment Report, and the STMD, or Space Technology Mission Directorate shortfalls. After mission definition is functional analysis. This is where we ask, what does the robot need to do? Does it need to deploy a payload, traverse through rough terrain, process or sample a spot? These functions come directly from mission goals, which flow down into concept of operations, which I'll ask you to develop. Then we move to requirement definition. Now we start to quantify things. How far should the robot travel per day? What terrain must it survive? This is where we bridge between aspirations and engineering constraints. We'll then write system requirements together. From there, we can shift to design drivers. What's going to constrain your system the most? Is it mass, the lunar night, communication delays? This helps us understand what's hard and what matters the most. I will ask you to identify mission, payload, and environment characteristics that impact your robot system. Now we explore the trade space, the many ways to achieve your goal. Do you use a 5 degree of freedom arm, solar power or RTGs, autonomy or teleoperation? This is the playground of engineering creativity. We will identify performance metrics to make design decisions based off. Next, we quantify those trade-offs. We weigh options based on criteria like mass, complexity, risk, and robustness. You'll learn how engineers make decisions by balancing competing needs through systems engineering techniques and tools. Finally, we will have arrived at our baseline design. This is your integrated mission concept, justified by your trade-offs and requirements. It includes the ConOps, the data product definition, system architecture, subsystem architecture, and maybe even component selection. Throughout the course, each of these boxes becomes a milestone in your journey as a mission architect. And by the end, you won't just understand the design process, you'll have applied it, start to finish, to a robotic mission of your own. Now that you've seen the design process from mission objectives to baseline design, let's talk about how we make sure what we build actually does what we intended. That's where the systems engineering and this V&V model come in. This diagram is known as the V model, and it captures a fundamental idea in engineering. For every design decisions we make, we must later verify that we built it correctly and validate that it fulfills the mission's goal. Let's walk through the left side first. Definition and decomposition. This mirrors the design flow chart you saw earlier. We start with a concept of operations, which you'll sketch out in an early assignment. Then we'll define system level requirements, like how far the robot needs to travel or how long it needs to survive. Those decompose into subsystem requirements, how much power is needed, what sensors are required, and how strong the chassis must be. Then comes component definition, specific wheels, motors, radios, solar panels, processors, all grounded in physics and performance. You'll walk through each of these layers in your course, writing requirements, analyzing subsystems, and making trade-offs based on mission needs. Now let's shift to the right side, integration and test. This is where the robot gets built and checked. We want to write requirements such that we can verify that we met said requirements in this phase. At the bottom, component verification ensures parts behave as designed. Did the motor spin as commanded? Did the thermal system stay within limits? Subsystem verification asks, does the power subsystem keep the robot alive through the lunar night? Can GNC keep the rover on course? System verification asks, if the robot can accomplish all of its functions: mobility, payload ops, comms, other integrated control. And at the very top is system validation. Does this robot meet the mission's original purpose? Does it answer the science question? Can it operate in the target environment? The V model ensures that every assumption and every requirement is testable and traced, from early paper sketches to hardware in the field. This is the requirements tracking spreadsheet you'll be using throughout the course to document your mission's objectives and system requirements. It might look like just a spreadsheet, but it's actually your bridge between design and verification. It directly supports the right side of the V model we just discussed. In systems engineering, we use this kind of matrix to maintain traceability, the ability to connect every high-level mission goal to a set of testable requirements, and eventually to verification activities. Let me walk you through some of the most important columns, which are highlighted in yellow here. These are required for every row that you create. This level tells us where a requirement sits. Is it a system-level mission objective, a subsystem function, a component specification? This connects directly to the left side of the V model, concept of operations to system requirements, all the way to component design. We track the level so we can later verify and validate the requirement at the right level. The objective or requirement statement is the heart of each role. It must be clear, specific, and measurable. Think the rover shall traverse 1 kilometer per day, or the sensor shall detect particles in the 0.3 to 3.3 mega electron volt range. This column anchors your design and feeds directly into test planning. The date last updated helps keep your process current and accountable, and signals when assumptions may need rechecking during subsystem integration or trade studies. Engineering documents evolve. Requirements change as we learn more. The reasons or justification is the context for the requirement. Why does the requirement matter? How does it relate to the mission goal or the environment? This is where you make the engineering case. It also helps during trade-offs. If you need to drop or change a requirement, this column shows the cost of doing so. The source is any reference document in which contextual information helped inform your requirement. Is it based on a scientific goal from the decadal survey, a stakeholder interview, a spec sheet? Citing sources supports transparency and prevents downstream confusion, especially if someone on your team challenges the need for a requirement. The system or subsystems affected helps note what part of the system this requirement impacts. For example, does this requirement constrain thermal design, power supply, or communications bandwidth? This helps assign ownership and plan verification tests correctly, just like how the V model assigns tests at the component, subsystem, and system level. And finally, the verification plan maps to the right side of the V model. How will you test this requirement? Through simulation, lab testing, in situ measurements, or inspection. For every requirement, we want a method of proof that tells us whether we've built the right thing and built it right. Throughout the course, you'll return to the spreadsheet as your design evolves. It will become your traceability matrix, something used across aerospace, NASA, and industry to ensure no requirement is lost and no test is misaligned. This is how professional engineers design with discipline. Now that we've seen how requirements tie into system design and verification, let's talk about how to actually write a good requirement. Requirements are not just vague goals or nice-to-haves. They are contractual, testable engineering statements that define what your robot must do and under what conditions. That means they need to be written clearly, precisely, and in a way that allows someone else who wasn't involved in your project to verify that it was satisfied. Let's look at the recommended structure for writing a requirement. The system, subsystem, or component shall perform an action under some specific condition or constraints with quantifiable, verifiable criteria, including units and tolerances if needed. For example, the rover shall traverse 1 kilometer per sol on 10-degree slopes with a maximum slip ratio of 0.3. Or the thermal control system shall maintain the battery temperature 2 within negative 10 degrees Celsius to 30 degrees Celsius for each lunar night. These are not just aspirations, they're testable criteria that trace directly into your verification plan. We like to write requirements in a way that we can explicitly define a verification method for that requirement. To guide us, we use 2 industry standard checklists to evaluate the quality of a requirement. On the left is NASA's criteria, and on the right is the SMART framework. Both emphasize similar things. NASA criteria include clear. There's no ambiguity in what's expected. Testable. Can you measure whether it was met? Necessary. Does it relate to the mission objective? Feasible. Can the requirement be achieved? Traceable. Linked to a higher level objective. And correct, based on sound reasoning and evidence. SMART goals are specific. They are focused and unambiguous. They're measurable, as in uses numbers, thresholds, or units. They are achievable, technically doable, realistic, doesn't ignore real-world constraints, and traceable, tied to the source and verified through testing. When you write your requirements in the course spreadsheet, you'll use this structure and check against these criteria. Think of it this way. If your robot fails during a test, someone will come back to the spreadsheet and ask, was the requirement unclear? Was it even testable? This is your design's legal backbone. In my experience, writing good requirements is a difficult task if you have no experience and thus no feedback from writing requirements. You can read about good requirements in theory, like through the NASA Systems Engineering Handbook, or listen to me talk about what I look for in good requirements. But after years of teaching about requirements, I think the best way to write a good requirement is through experience, iteration, and feedback. For all of the requirement assignments, you are more than welcome to write your requirements independently, iterate with a classmate, and request feedback from me, but I have a proposal for you. I have crafted a custom GPT called Space Robotics Requirements Guide, so that every student can iterate with and get feedback from a chatbot about their specific project on demand. To use this bot, you need to either sign up or log into a ChatGPT account. I can't force you to do this, and you can still submit the assignment without using the tool. But let me tell you, I tried the tool multiple times to help refine vague requirements or untraceable requirements, and the guide actually did steer me towards requirements that met all the NASA and SMART criteria. Regardless, your requirements will be verified along the metrics of clear, correct, feasible, verifiable, necessary, and traceable, regardless of how you come up with them. To wrap up this lecture, I want to give you a preview of the major assignments you'll be completing throughout the course. These are mapped directly to the system design process we've been exploring, from defining your mission all the way to designing and analyzing subsystems. Let's walk through each of these assignments in order while looking at the flowchart on the right hand of the slide. For the gap assessment, you'll start by exploring current NASA roadmaps and identifying open scientific and technological gaps that interest you. This will help you define your unique contribution. For mission definition, you'll choose a planetary body, state your mission objective, and describe what kind of robot is needed. For payload assessment, you'll ask, what instruments are necessary to meet my mission objective? How do they constrain your design? For the concept of operations, you'll answer the questions, how does your robot operate day to day? Who commands it, when, and how? What are its timelines and events? For operator interaction, you'll consider how much of the system should be automated versus controlled by humans. For the data deliverable definition, you'll ponder, what will your robot measure or return? What's the data product that supports your science goal? For system requirements, you'll translate your concept of operations and payload into concrete system-level requirements, both functional and non-functional. For subsystem requirements, we'll define all of the subsystems in Module 3, but then you'll think about what these various subsystems need to accomplish. For component requirements, you're going to further flow down subsystem requirements into requirements on specific components. At the design solution research stage, you'll research potential options for each component and subsystem, identifying multiple viable candidates. For decision matrix definition, You'll create a trade space and develop criteria, such as mass, cost, complexity, etc., to compare and down-select design options. For component selection, you'll commit to a baseline design of various components, supported by data and trade-offs. For subsystem diagram, you'll visually represent how components interface and flow within a subsystem. And finally, for subsystem analysis, you'll analyze the performance, risks, and design maturity of that subsystem. And by the end, you'll have a baseline design for your space robot. In this lecture, I hope that you've come to understand how to design a space robot from mission objective to system architecture, leveraging systems engineering.